This video explains how to calculate the stresses in compound cylinders made of different materials when subjected to temperature change. When a compound cylinder composed of different materials experiences a rise in temperature, the diametral or circumferential strains at the interface radius will differ due to the distinct thermal expansion coefficients. As a consequence, there will be a change in the interface pressure.
Figure 1 here illustrates a compound cylinder with a total shrinkage of delta 1, at temperature T1. The amount of compression in the inner cylinder, and the amount expansion in the outer cylinder are dependent of the material properties.
Figure 2 illustrates the same cylinder when its temperature is raised to T2. In this case, we consider free thermal expansions first. Because of the different amounts in thermal expansions, the shrinkage becomes delta 2. Finally, the common interface must settle in between the total shrinkage allowance or the overlap. To happen this, the outer cylinder should expand whereas the inner cylinder should compress. This will finally create a new interface pressure. The amounts of expansion and the compression of cylinders depend on the material properties. Let us now see how to relate free thermal expansions of the two cylinders to the interface pressure. The difference in the free thermal expansions can be written as R times alpha B minus alpha S, multiplied by the temperature change, delta T. Here, alpha represents the coefficient of linear thermal expansions of the materials. R is the common radius.
The compression and the expansion of cylinders, resulting from the restriction imposed on each cylinder, are denoted as EES for steel, and EB for brass. These deformations cause a change in the interface pressure.
Now consider two elements on the surfaces at the common radius as illustrated here. The element A is on the inner cylinder, and the element B is on the outer cylinder. The enlarged views of the stress elements are shown on the right. The value of sigma R represents the interface pressure, which is common to both the elements A and B. Note that we have marked all stresses as positive, that is tensile. But in reality, the stresses subjected by the inner cylinder are compressive. When you substitute numerical values, you need to consider the correct sign. For each of the stress elements we can write equations for deformations in terms of stresses. First, for element A, EB is equal to R times strain, that epsilon B, which is equal to R divided by modulus of elasticity, multiplied by sigma R minus nu times sigma HI. In these equations, the subscript B is used for brass cylinder, which is the inner cylinder, and the subscript S is used for steel, which is the outer cylinder. A similar equation is written for outer cylinder as well. As we pointed out before, the sum of these deformations should be equal to the difference between the free thermal expansions. By doing this we obtain a relationship between the interface pressure and the hoop stresses at the common radius, as given here. Graphical representation of stresses using the Lames relationships can be done as illustrated here. From this plot of stresses, we can obtain two relationships relating the hoop stresses at the interface to the interface pressure. Then, with the use of the relationship we derived incorporating the thermal expansions and the interface pressure, it is possible to calculate the interface pressure and the hoop stress values.
Watch the video on stresses in compound cylinders, if you are not familiar with the graphical representation of Lames equations. The link to the video is available in the description below.